Hello and welcome to this third stage of the Statistics e-course. My name is Rosanna Breen and today I'm talking about features of experimental designs. We're going to cover 5 main things in this presentation. First, we're going to look at different types of data, and the reason that's important is because different types of data are appropriate for different types of tests. We're then going to look at relationships between variables, for example correlations and chi-squares. We're then going to look at differences between groups, how to choose a test for difference between groups. Do I want a t-test? Do I want a Mann-Whitney test? We're going to look at types of data required for a t-test. In particular, it's important that we use parametric data for a t-test, so we're going to revisit some of the assumptions behind parametric data and how this differs to non-parametric data. We're then going to look at non-parametric tests separately. Then we're going to look at critiquing experiments. So when reviewing somebody else's study, what do you need to consider in being able to critique that experiment and identify whether it was robust and reliable and so on. Finally, we're going to look at one versus two-tailed tests. So in other words, we are interested here in whether we have a hypothesis about the relationship or the difference between the group. If we do have a hypothesis, for example, we believe that people on our maths skills course are going to do better on their maths exams than those who took a confidence building course, then we do a one-tailed test. If we didn't know what the difference was going to be between these two groups on their exam scores, we would conduct a two-tailed test. Often it's the case that SPSS will simply run the analysis for you and then you can identify at the end whether you want to interpret that result as a one or a two-tailed test. We'll go into that in more detail later. So there are 3 levels of data then which may determine what statistical test you use. Interval level data is required for many statistical tests, and that means that the distance between points of your scale should be equal at all parts along that scale. For example, exam scores and age. So a Pearson's correlation, for example, and a t-test would require you to have interval level data. Ordinal level data has an order to it, but the distance between the points of your scale is not equal at all parts along that scale. So for example, exam grades. The range of scores that are included in a grade A is usually a bigger range than the range of scores included in a grade B. So the types of analysis that we would do with ordinal level data is, for example, a Spearman's correlation. Nominal level data consists simply of named categories, so men versus women, math skills versus confidence building skills, groups, pass or fail. And with nominal level data we would usually use a chi-square test to look at a relationship between these different variables. So another thing to consider is whether your variables are continuous or categorical. Continuous variables run along a continuum. Categorical variables, which are also called grouping variables, just describe categories. So for example, categories of people. All of these examples are called variables simply because they're all things that vary in the data set. But the type of data is important to identify in order to identify the right kind of test. So what do we do if we want to know whether there is a relationship between variables? Well, if we have continuous measures, we can use correlations. So for example, we can look at whether exam scores correlate with academic confidence. But if we want to look at associations between variables that are categorical, we use the chi-square test. So for example, if we're looking at whether men and women have different chances of passing or failing depending on whether they have undertaken confidence building or math skills training, then we'd use a chi-square test. So here is a slide that might be worth revisiting later or taking some notes on now. This helps you to choose a test for relationships between variables. If your data is interval level, then you use a Pearson's correlation. This data must be continuous, it must be parametric. for example exam scores. If you have ordinal level data, then you can use a Spearman's correlation. In this case, our data is categorical and non-parametric, so for example grades. And finally, if you have nominal level data, you use a chi-square test. In this case we also have categorical data, but they're not related to each other, they're nominal level, just named variables. Let's go on to looking at differences between groups. Well, we use t-tests often, and we like that because parametric data is good, it is very detailed data, but we may have to use Mann-Whitney or Wilcoxon-signed rank tests if our data is non-parametric. We also need to consider whether we're actually comparing people or conditions. If we're comparing two separate groups of people, we use a between subjects analysis. But if we put the same group of people into two different conditions, for example hot and cold weather, to look at whether their exam performance is enhanced by hotter or colder weather, we'd use a within subjects analysis. So here's another slide that helps you to identify which test you use for differences between groups. First, look at whether the data is parametric or not. If it is parametric and you are looking at two different groups of people, that's the between subjects analysis, and you'd use an independent samples t-test to test for those differences. If you have parametric data, but the people within your sample have been subjected to two different conditions, then you'd use a paired samples t-test. If your data is non-parametric, on the other hand, and within subjects, then you use the Wilcoxon-signed rank test. And if you have two groups of people, but non-parametric data, you use the Mann-Whitney test. Let's look in more detail at a t-test then. To actually conduct a t-test, we need an independent variable and a dependent variable. An independent variable is the one that is manipulated by the researcher. So in my study I have put students into two different training environments. One has undertaken math skills training and the other have undertaken confidence building training. A dependent variable, on the other hand, is a variable that's expected to change as a result of the independent variable. So we're interested in whether these two different conditions or two different groups are going to have any effect on their academic confidence or on their exam scores, and these variables are dependent. The dependent variable must have parametric data. The independent variable is a categorical variable. The dependent variable must be parametric to conduct a t-test. Let me remind you then about the assumptions that parametric tests have to meet. The data must be normally distributed. We've looked at that in previous elements of this course. The variances between groups must be homogeneous, so that means that the way in which the scores vary from the mean must be the same in the two groups. The data must also be continuous and interval level data. And finally, the data from different participants must be independent, so we can't have the data from one subject influencing the data from a second person. Non-parametric tests don't require the data to meet these four assumptions, and that's why they're often called assumption-free tests. They are less powerful because they convert the data into rankings. You'll remember when we talked about the median, that is also a less powerful statistic than the mean because it also converts the data into rankings. So by doing that, you lose some information about the magnitude of the difference between the scores. A type 2 error is more likely to occur with non-parametric tests because we're more likely to think that there is no difference between groups when actually there is. Have a look at the data in our data set and decide what level the data is at, nominal, ordinal or interval, and send me your thoughts by email. Critiquing experiments. Well, first of all, it's important to ascertain whether the experimenter has obtained consent. Written consent is required for participation in most experiments, but there may be specific ethical requirements for your field of work that it's worth being aware of. Were there any possible sources of bias? Well, particularly with repeated measures tests where you have a within subjects design, where you have the hot and cold weather example, for example. If students have undertaken the exam in hot weather and then undertake the exam in cold weather, they may have some practice effects from having done the exam once and then having a second opportunity. They may do better the second time. People can also get bored if they're asked to repeat questionnaires, within a few days of doing it. It's worthwhile really spreading out the application of questionnaires because people, the boredom factor can slip in. Finally, it's worth looking at whether the experimental sampling strategy was adequate. Was it randomised? Did they randomly assign subjects to the various conditions? And were there enough subjects in there for conducting tests of difference? When we're interpreting our SPSS outputs, we'll get a degrees of freedom statistic. SPSS uses this to calculate the exact probability that the statistic result, for example the t-test, could have occurred by chance, and it's always important to report the degrees of freedom, the statistic result, and the p-value. You'll find the p-value under sig brackets 2-tailed in any of the SPSS outputs. That gives you the p-value for a two-tailed test. P refers to probability, that is, the probability that the statistic result could have occurred by chance. So if p is less than 0.05, then your results are significant at the 5% level. That means that there's less than 5% chance that this result was purely by chance. There's a 95% chance that this was influenced by your experiment. If it's statistically reliable, significant at the p less than 0.01 level, then that's a really good result, and that shows that the result is significant at the 1% level. We normally report whether our results are below the 0.05% level or the 0.01 level. Finally then, one versus two-tailed t-tests. A one-tailed result is reported if you predicted the direction of the correlation or the nature of the difference in advance of conducting the test. So for example, if you had a prediction that people who are more confident about studying statistics will do better in their exams, then you report a one-tailed correlation result. A two-tailed test is required if you didn't predict the direction of the correlation. So if you're not able to predict whether men or women will score higher on the academic confidence scale, you report a two-tailed t-test result. Most tests in SPSS report a two-tailed p-value. If you want to obtain a one-tailed p-value, just divide the p-value by 2. I'll show you that when we do a demo next. For now though, congratulations, you've completed the third element of this course. You will receive a link to a t-test demonstration using SPSS. You can keep referring back to this presentation when you have a look at these t-tests in action and have a go yourself.